All right. So this is a continuation of last meeting's lecture. We're covering a paper called "A Quantitative Study of Locality in GPU Caches for Memory-Divergent Workloads." We're currently at the results section. The previous part had until pretty much all the context, but to kind of summarize pretty quickly of what we should know so far is that GPU caches are pretty much shared by a large number of threads, and this causes a lot of thrashing due to high contention. The contention and thrashing is overwhelmingly seen in a certain class of applications called irregular applications, which are applications that either have a large amount of memory or control divergence. And what that essentially means is that within the same warp or different threads that are running parallel cannot their requests for memory or are pretty wide apart in terms of memory addresses, so they can't be all coalesced into one single transaction. But a common approach used in CPU optimization to kind of help in optimize the performance of the CPU is taking advantage of spatial and temporal data locality. But due to the high contention of cache resources, we need to ensure that GPUs are actually bringing in cache lines that exploit spatial and temporal data locality and not just overfetching cache lines, leading to more thrashing and less optimal cache utilizations. Modern, or at least at the time of this paper, GPU architectures employed sectored or segmented cache lines that allow the cache line to hold data from, not more data, but data from different places, from different memory addresses, while also taking advantage of temporal and spatial locality. So pretty much how it works is that the GPUs, at least referenced in this study, they have a cache line size of 128 bytes, and in a sectored cache line, you would pretty much see that cache line split into four 32-byte segments. We also know that just like cores in CPUs, we have streaming multiprocessors or SMs in GPUs. And in terms of architecture, CPU cores have their own personal L1, L2 cache, registers, buffers, and missed status holding registers, while each GPU SM has its uh, own thread independent registers, L1 cache, and shared memory. And we can kind of see this over here. There's like a whole diagram of the typical memory hierarchy in GPUs. We also have the L2 cache, which we'll be discussing quite a bit, and that's shared across all of the SMs on a GPU. Other than that, fundamental unit of execution for GPUs is warps, while CPUs is threads. What a warp essentially is that it's a collection of 32 threads that are running the same instruction in parallel. The reason that CPU cache optimization doesn't really map one-to-one in GPUs is because due to the large amount of threads executed by the GPU simultaneously, the cache is diluted to pretty much mere bytes per thread. So we can see that over here. So as opposed to in CPUs, where you would see kilobytes per thread, in there's a much scarcer amount of memory available per operation in GPUs. If you see here for L1, we see that rather than kilobytes, there's just mere bytes. Um, so 32 bytes for GTX 580, so on. And for L2, which is a little bit larger and shared, you have a couple more bytes per thread, but not too much usually. Um, so yeah, what this means is that due to the scarcer amount of memory available per operation, the massively parallel execution of these threads means that there's a greater level of contention and thrash that makes cache line reuse through spatial and temporal locality much harder to achieve. What this study tries to do is it tries to establish quantitative metrics to kind of define the spatial and temporal locality, just overall locality across these diverse irregular workloads. If you see over here in table 4, we have like a bunch of kernels that they run and they compare to each other, and they try to kind of I don't want to say optimize, but they kind of try to find like the most memory divergent workloads possible um, to run their quantitative tests on. Um, so what we see is that across irregular workloads such as these, with varying levels of memory divergence, the maximum exploitable data locality in GPUs, if cache size wasn't a bottleneck, is primarily what's being memorized. Sorry, not memorized. Being quantitatively measured here. So to do this, they over here they pretty much describe that they use a GPU simulator to simulate actual GPU conditions, as well as the metric that they use for defining memory divergence. You might ask why they don't run the experiment on live GPUs, but the reason for that is because one of the aims of this paper is to find out the maximum possible exploitable spatial locality, temporal locality, and in order to do that, they pretty much simulate a GPU with infinite cache size for both L1 and L2 cache. But yeah, so coming back to this metric, they use this metric called coalescing efficiency to define the memory divergence of an application. And this coalescing efficiency kind of comes from the fact that GPUs tend to try and combine the memory instructions across threads in a single warp into the smallest number of memory transactions possible. And in this case, memory transaction just means accessing data from the cache. So the memory divergence of an application can be defined as the number of instructions, which is GMI. So you'll see here total global memory instructions. And you can divide that by total number of global memory transactions. And what this essentially means is that if for 32 instructions, for example, one warp has 32 threads, and each of these threads are running their own instructions. So you have 32 instructions per warp. If you can pretty much take all of the memory addresses needed for all of the 32 instructions in a warp and kind of compress it into one cache line call or one memory transaction, which again, accessing data from higher levels of memory. If you can pretty much coalesce it is the term that's used. But what it essentially means is combine all of this into one call or transaction. You would have a perfectly coalescing kernel or program. So what they do is that over here they describe how they normalize this. So you can also have a wildly memory divergent workload, which in that case, for each of these 32 threads, for each individual thread, you would have to have a memory transaction. And what that essentially would come out to is 32 over 32. And how they normalize it is they divide it again by 32 to get a percentage. So for example, if you had a perfectly coalescing application, you would have 32 instructions, but only one transaction. But if you had and then if you divide that by 32, you would get 100% coalescing efficiency. Mm-hmm. But if you had a very, very memory divergent workload, you would have for 32 instructions, you would have 32 transactions. And that comes out to 1, and then you divide that by 32, and that gives you approximately a 3% coalescing efficiency. And you see this kind of used over here to kind of define the memory divergence of each of these kernels. So to go on, I think that's most of the context that you'll need. So the first thing that they try to do is they try to understand the cache line reuse in the L1 cache under the realistic conditions, under the current GPU, or at least at the time of the paper, GPU cache size constraints. And they try to understand how much cache line reuse is possible if cache size wasn't a bottleneck. So what they do, what this allows us to see, is the level of cache line reuse that we can optimize for within GPUs. We'll see over here in the first diagram, they have an L1 cache that has 16, six. I'm trying to highlight this. I guess I can. It's not text. But yeah, 16 kilobytes of size, where they see that across all of the CUDA kernels that they run, only 43%, only 43% of cache lines are reused, which means one of two things. Either the cache line is never ever re-referenced, or it's evicted before it can be re-referenced. And to find out the maximum possible cache line reuse, they run this again with a cache that has infinite size. And what they find out this time is that the cache line reuse is at about 70%. And what this shows us, as seen in observation 1 here, is that there's a much higher reuse possible than currently exploited by GPUs. And this might primarily be due to the fact that that memory or cache size is a bottleneck. But to kind of the whole point of this is to kind of see just how many cache lines are actually re-referenced and how many cache lines are never re-referenced. So what this says is that 70% of the cache lines are re-referenced. So if we were to have a larger cache size, we would be able to optimize for this. But due to the cache size constraints, we only see 43% cache line reuse. What this also shows is that even with infinite cache, 30% of the L1 cache lines have no reuse. And what that means is that there's segments of these cache lines that are overfetched. And what this is doing is it's taking up bandwidth in terms of network on chip, or if we look further, we'll see L2 cache as well. But yeah, going on to section 4.2, section 4.2 goes into spatial locality. This is pretty important because, as said here, GPUs have a wide cache line size of 128 bytes, and we see that threads threads from warps tend to access data nearby to the data accessed by another thread in the same warp. So what this section really aims to do is quantify the spatial utilization of cache lines to find the potential optimizations in cache design. So we'll see over here 4.2 in section 4.21 spatial utilization limit and overfetch. Also, I'm going. I don't know if there are any questions. I can't really see the Zoom.
Yes.
Does anybody have any questions so far?
Yes, Shreyas, can you hear me?
Hello?
Yeah.
Hello?
Srini
no, I cannot. Oh, have I just been droning on? Oh my.
Can you hear me, Shreyas?
Yeah, I didn't realize that I didn't hear anybody. I figured.
Okay, that's okay.
Yeah, let me try rejoining. I don't know what's up with my audio.
Well, obviously
today.
Now you're hearing him.
Yes, now you can hear me. That's okay.
It's all good. Sorry about that.
No, so there's only one comment I wanted to make. It's actually just very recently. If you scroll up a little bit, in the previous section in the paper. The 70% versus 43%. Shreyas, can you hear me? Looks like he can't.
I think he's frozen.
Yeah.
Oh, he said he was going to rejoin. Okay, yeah, I think
Hmm.
he will come back.
Okay.
Let me see. I think I have a copy of the paper up, if I'm not mistaken. Let me see if I've got. Let's see. If I
He's
were
still
to.
he's still showing on my screen.
Yeah, yeah,
Yeah.
he said he will try to rejoin. That's what I heard. I thought I
Yeah.
heard.
Let's see. Okay. Well, in the interim, can you guys see this?
Yes, we can see that.
Okay,
Yes.
cool. So there was what was the, um, um, um,
It was in section 4, Warren.
section 4. All right, let's hop down there. Cache lines reuse limit. Let's see, 43 and 57%.
No, it's down. It's a little bit more down.
Mm-hmm.
Yeah. There it is. The last one. Observation 1.
Much higher
That's the one.
reuse currently.
Yeah.
It's
My only comment here was I was going to make a comment. I don't know if I want to wait for Shreyas. He will probably rejoin.
hmm,
The comment is this whole study. Okay, so he's calling me. Hold on 1 minute.
okay, no worries.
Hey Shreyas,
Hi.
are you
I
not able to rejoin?
no, I'm able to rejoin. I just kind of wanted to gauge the.
No, 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 no. You are on the speaker here. So if
Okay.
Yeah, I don't.
if you're okay.
Yeah. So I will try coming back in
Okay.
from. Uh,
Okay. So we'll see you soon.
yeah.
Come back in. Yeah. That may
Yeah.
fix your audio issues. Okay, see you soon. Bye. Yeah, the comment I was going to make was that if this is going to, as a feedback to people that design cache sizes, say at
Hmm.
NVIDIA, um, I would be a very happy camper with that number, right? I mean, see, with infinite cache size, you are getting a 70% reuse, whereas with my design, which is a modest cache size, I'm still getting more than half right there. Um, so that's the comment I was going to make. Um,
You mean that you have a memory allocation strategy on like a GPU that you've designed that has a better cache reuse than what's being outlined in the paper? Is that what you're saying?
no, what I'm saying is, see, we obviously cannot have infinite cache size. That is
Mhm.
theoretical, right?
Hmm.
So even with that, if you're only getting 70% reuse, and with my current limited cache size, I'm getting more than half of that reuse,
Hmm.
43%.
Hmm.
Um, I think that's a fairly decent number to go with
Yeah, I
in
So
mean,
you're
terms of
saying the performance
cache efficiency.
is good, in your
Yes,
opinion?
exactly,
Okay.
exactly. With that cache size.
okay, so yeah, let's see. Memory divergent workloads do have reuse. Cache hierarchy and warp scheduling are not aligned to exploit the locality. Contradicts the common assumption that irregular workloads inherently lack locality.
Hmm.
Hmm. 40% of possible cache reuse is lost due to eviction before reuse occurs. Okay, sure. Checks out. More memory traffic than needed. Uh, let's see. Limited per thread cache, high contention. Useful lines are evicted before reuse. Then we could improve replacement policies and track longer term reuse. Warp scheduling could prioritize warps that share data if the lost locality is mostly temporal. Bigger or
Oh, he
dynamically
might.
persistent
Yeah.
caches could pay off for divergent workloads if the issue is the cache size being the limit of the reuse, and then evictions are happening too early. So if you were to prefetch or keep certain lines resident longer, then you might be able to exploit some of that extra headroom.
Okay, it looks like Shruras,
Great,
are you
back.
back?
Yeah, I hope you guys can hear me now. I can hear
Yeah, we
you,
can.
but I hope this doesn't. I don't know what's wrong with my laptop. I've been having this audio issue for a while. I thought I fixed it, but apparently not. But yeah, so I'm free to answer any questions anybody may have had while I was droning on. Um, so yeah, let me just share
Yeah.
the paper
Okay.
again.
Okay. Can you hear us now? I thought you said you couldn't.
Yeah, I couldn't hear anybody. I
Okay,
don't
but
know
you
if you
can
guys
now.
could hear me, but
Yeah,
I
Yeah,
we
couldn't hear
heard you,
anybody.
We
right?
heard you.
It's
Yeah.
just that,
yeah.
yeah, it's
Okay.
just that when I try to speak, make a comment in section 4 about the 70% versus 43%, you couldn't hear us.
That's no
Yeah.
problem.
Okay. Yeah. Okay. All right. So yeah, any comments, questions, anything that I need to go over, answer?
So this is circa what, 2024,
21, I
20,
believe,
21, 22 types of.
2021.
Yeah, because I was
or
just looking at the.
2022. So
Yeah, okay, yeah. I was just looking at the
received
GPU
2021.
models. Yeah, okay.
Yeah,
They seemed
published
rather
22.
old. Okay.
Yeah,
Yeah.
so that's why I was making sure to say that at least when I was referring to modern architectures, I was referring to modern architectures at the time of this paper, because
Okay.
I do know that there's like Ada Lovelace, Blackwell, that this
Hmm.
paper doesn't consider.
Yeah, yeah. Okay.
Yeah.
But is still the cache usability, what was it, 40-ish percent, 40 to 50 or something? Is that still considered to
Uh,
be a
so
good figure?
So, in terms of cache line reuse, I mean, ideally you'd want it to be at 100. So 40 is pretty poor. I don't know what the benchmark is normally, but what the paper establishes is that optimally, right? If you had infinite cache size, the maximum amount of cache line reuse that you're going to see
Hmm.
across all of these workloads is 70%. So if we look at the graph over here, right, we see some at 100% reused, right?
Hmm.
We see some at 100% not reused. But what we see is that this is ideally what we want. And if we look at the cache line reuse in the GPU simulated with limited or 16 kilobytes um, of cache size, L1 cache size, right? We see that the same kernels that are showing up as 100% reused here are near
Hmm.
100% not reused,
Right.
right? So what the paper is trying to find is what is the ceiling for the amount of cache line reuse we can see across all of these applications? If and what having an infinite cache size allows for is that once a cache line is brought in, uh, it'll never be removed. So one of the biggest constraints with a small cache size or a limited cache size is the fact that in order for the other instructions to run, especially on memory divergent workloads, you're going to have to fetch other memory addresses. And when you try to bring these memory addresses into the cache, something that you might need to reuse later on is going to get replaced. It's going to get kicked out, right? So yeah, I don't know if I explained that well, but that's the basic premise of what they're looking at here.
Okay. Thanks.
Yeah, I have my I just chat GPT what the landscape is like these days. And they were like the verdict seems to be like we're essentially just like immediately identified that that was the problem and are trying to serve a lot of inference. So there's a lot of people like pushing on that at the moment. Seems like 92% was the figure it pulled. I didn't check it, so but
Okay,
seems like
okay.
the work's being
So you're
done.
saying The 92% that's their hit rate on the reuse?
Yeah, so aligning warps with the NUMA layout of AMD's MI300X chiplets boosts the L2 cache hit rate from 43% to 92%.
Hmm. Is that a real system or a theoretical one or some experiment somebody's doing or?
That is that is part of the architecture of one of AMD's new chips, is what they're
Hmm.
saying. Yeah. Seems like
So
cache reuse is something AMD is kind of like zeroing in on at least.
got it.
Like both all the hits are AMD stuff at least.
Yeah. Okay. Thanks.
Mhm.
Yeah. So yeah, that's the basic premise of this section. Um, yeah. So what it finds is that across all of these kernels, 70% is the max that you're going to see. But what this means is that for the other 30% that isn't being reused, what we'll see later on in the paper is that the paper pretty much says that the current GPUs at the time they bring in sectors of cache lines based on demand. So if an instruction needs it, it brings in pretty much everything adjacent to that. But sometimes what it fails to predict is that, okay, I might need more than these 32 bytes that I'm bringing in. How much more, right? Because if you bring in a 128 byte cache line and it's never reused, you're wasting a lot of space. And that's going to cause for overfetch. That's going to cause extra load on knock and a bunch of other resources. But yeah, so what this first section is trying to show is that maybe there's space for improving the spatial and temporal utilization, especially for GPU, such that we can push this number of 70% average to be 100%, such that anything that is present in the cache is going to be there if it needs to be reused and only evicted if it's never ever going to be re-referenced, or if a certain segment that of if a certain segment of a sector or a certain segment of a 128 byte cache line is known to never it's known that it's never going to be used, right? It's never going to be referenced, then we just don't bring that in. So yeah, ideally this should be at 100%. But yeah, so to go on, one of the things that they try to look at and quantify is spatial utilization. And what this essentially, how they do this is they look at when a cache line is brought in, what is the initial utilization? So we know that for GPUs, or at least in this paper for a GPU, there's 128 bytes of cache line, right? Of these 128 bytes that are brought in, uh, what is the average amount of bytes initially used? And what we'll see is this figure 3 goes through L1 cache. And what we'll see is that for many, what it shows is that for many kernels, there's a very similar initial and final utilization, and only certain kernels have a higher final spatial utilization. But
Hmm.
at a 16 byte size, what we see is that the average initial and final utilization of cache lines is 46 bytes and 65 bytes, meaning that on average, 63 bytes from the time that a cache line is brought in. So from the time that 128 bytes are brought in to the time that the same 128 bytes are evicted, only about half of that cache line is actually being used, which means that there are 63 bytes worth of overfetch. And they yet again emphasize that This takes up stuff like network on chip bandwidth, L2 data cache bandwidth, and pretty much just lowers the performance of the system. So low specialized cache could also be due to limited and high contention, as a cache line may be evicted before it gets re-referenced. So say we okay, so they did the infinite size simulation as well. And what they saw is that the final utilization, obviously the initial utilization is going to be the same, but the final utilization with infinite cache size comes out to about 81 bytes, which is 24% higher than the 65 that we saw. That's the final utilization of the entire cache line at eviction. And we see that even with infinite cache size, right? There's still 36% of the cache capacity that is wasted. So those 47 bytes or so is wasted, which they're essentially, the authors say there's potential for further improvements in cache design, and they go on. So pretty much they draw two conclusions, and the first one is that the low spatial utilization of these cache lines, these 128 byte cache lines, kind of justifies that it's valid to split these cache lines up into 32 byte segments. And these 32 byte segments can be utilized to bring just the data that we need, rather than a bunch of data that's just going to sit there and clog up the system. So on the other hand, the much higher final spatial utilization, so this 81 byte, this figure of 81 bytes, shows that there's space for optimizing cache design. And what they pretty much recommend in the paper is to use a spatial locality predictor. So you pretty much go through a kernel and you try to find out how much spatial locality you're going to see from instruction to instruction, and pretty much you bring in a relative that same relative amount of spatial data into the cache to kind of prevent overfetching, but also underfetching, such that you will need to have another memory transaction to bring in your missing data. So they did this with L2 cache as well. And what they saw is that L2 cache actually performs a lot better. So even at the normal at this time of the paper 128 kilobyte cache size, we see that the final utilization of cache lines goes from 54 initially when the cache line is brought in to 85. And that means that 35% of the L2 data cache capacity is wasted, even with just default configuration. And what we can see is that this 35% figure is better than L1 cache, which is 36%. And that's L1 cache with infinite size. So L2 cache, because of the fact, and the primary reason for seeing a lot better spatial utilization in L2 cache, even under normal conditions, is the fact that L2 cache is shared between all the SMs, which means that any thread from any of these SMs, from any of these warps, right, is free to access the data in the L2 cache if they need it. So I mean, they go on to say that the average final utilization of cache lines is 95 when they redid the experiment with infinite cache size, and this is pretty much 2 times as much as the initial figure, which is 54. And the big difference shows that for it's well, what overall they find out is that pure sector based fetching works, but works to an extent, and a huge bottleneck in kind of increasing spatial utilization, especially in terms of L1 cache, is the cache size itself. But I mean, obviously you can't have infinite cache size. So what they suggest is to kind of have a mix of between pure demand-based sector fetching and just completely, fetching everything around the memory address that you need and trying to maximize. So there needs to be some semblance of a middle ground, and that that is much more the case for L1 cache as opposed to L2 cache. So they say here the analysis shows that we need more aggressive policies to properly utilize the L1 cache as opposed to the L2 cache, because the L2 cache does phenomenally well under normal conditions without the infinite size, and the buff that it gets from infinite size is about 10 bytes. Well, if we see L1 cache, it's about I want to say it goes from 65 to 81, I believe, right? Yeah, 81, which is, I mean, close to 16 bytes. So we see a lot more of a increase there. So going on, section 4.2.2. So, oh, sorry. So yeah, they do that for both L1, L2, and then in this section, what they try to do is they try to figure out, okay, so we see spatial utilization in both of these caches. Where do we see most of the spatial utilization coming from? So when we're building a spatial locality predictor, right? What should we be optimizing for? Are we looking at should we be optimizing for addresses for threads within the same warp, threads from different warps, but within the same CTA or thread block? A CTA or thread block, I forgot to mention this prior, but a CTA or thread block is kind of a bunch of warps together. It's a unit of scheduling. So essentially, a bunch of warps can be put together in a thread block, and that one single thread block is then assigned to an SM on a GPU. So when GPUs are assigned stuff or GPU SMs are assigned stuff, they're not assigned in terms of warps; they're assigned in terms of thread blocks. So yeah, so CTA is just the NVIDIA version of thread block. CTA and thread block are synonymous, pretty much. So what they're trying to figure out in this section is, okay, do we see a greater amount of spatial locality to be utilized between CTAs, between different CTAs, or within warps in the same CTA? So that's like the general premise of the section. And what they find out for L1 cache at the warp level, which is over here. I don't know, it's kind of weird. The whole paper has a very weird orientation of graphs, but for this section, this is the intra and intra-warp spatial utilization of L1 data cache. And there are 4 lines, as you can see. One is initial cache line, which we already know what it is. So when a cache line is brought in, how many bytes of those 128 bytes are actually, being used. And then final cache line, which is pink, is just upon eviction, how many bytes of that cache line has been used before it gets evicted. But then we have 2 new values here. Final intra-warp cache line utilization, which intra-warp essentially refers to, okay, so you have a thread, how much spatial utilization are you seeing, or how much utilization of this cache line are you seeing at eviction from threads within the same warp? That's what intra-warp is. And then this one is final intra-warp, which is essentially how much final utilization are you seeing across threads that are outside of the same warp as a thread that brought, or an instruction that brought in the cache line initially. So over here we see that.
Excuse me for just a sec here.
Yeah, go ahead. Yeah, go ahead.
All right. So the intra warp. I'm trying to get the inter terminology here. So the inter is that the same problem that, or in both cases, I guess it's the same code that it's executing. Is that correct?
Yeah, yeah. I mean,
Okay.
this is all one run. They
Uh-huh.
just try to find well, probably not one run. I don't know exactly how they ran it, but this is all
Hmm.
like pretty much same program, same data. But what they're including right now is just two more values that are saying, okay, so you have an initial utilization and you have a final utilization.
Got it.
So of this final, at the time of eviction, how much utilization are we seeing across all of the threads within the same warp? And that's
I see.
intra warp, right?
Hmm.
And inter warp is how much utilization are we seeing across threads from that are outside of the thread's own warp, right?
So
Uh,
is that just saying if you had higher interwarp versus intra-warp, that would mean that it's staying on the particular problem longer or the data for that problem? What is that telling me about that? I guess.
I guess it's
um,
telling you that the locality of
Yeah.
the group within that warp is good, right? Meaning you're reusing the threads within the warp
Are
are
we using
reusing
the
the data
data?
much
Are they?
better. Yes.
the paper defines two levels of locality, warp and CTA. The one issue that I do have with this paper is that when they refer to interwarp, they don't it's pretty much just any thread that is um outside of the thread that you're initially referring to, or the yeah. So for a thread that brings in a certain cache line, what it's saying is that interwarp is essentially a thread from any other warp within the same SM. So this could be a warp within the same thread block. So as I said before, thread blocks are pretty much a collection of multiple warps. So it doesn't clarify until a little bit later, that whether it doesn't clarify it, because interwarp is just referring to a thread from any warp that is not the same warp as the thread that they're looking at that brought in the cache line initially. I don't know if that answers your question, but I don't think a higher amount of interwarp cache line utilization shows that it's more busy, but it just shows that there's the localization is well enough such that there's another thread within the same SM that is using the data stored in the cache line, whether that's in the same CTA or in a different CTA. I don't know. Does that make sense?
Yeah, I'm trying to kind of visualize it here in my head, but yeah, I guess it. Yeah, I guess it does. Go ahead and continue, and I'll see if I'm understanding it correctly. I don't want to hold everybody up,
Okay.
you up.
But yeah, so they look at the intra and interwarp spatial utilization for the 16 kilobyte cache. It's pretty much the same kind of structure throughout. They'll test the same conditions both with infinite and 16 or 128 kilobyte cache. But yeah, so specifically, they're looking at L1 in this graph over here. And what they see is that for intra warp spatial utilization, or spatial utilization seen within threads from the exact same warp, it's about 52 bytes of the cache line is being used by uh, all of the threads that are in the warp, in the same warp as the initial thread that brought in the cache line. And it also shows a interwarp spatial utilization, or for all of the threads outside of the same warp, within maybe the same CTA or a different CTA, 60 bytes of the cache line are being used. So when they read the experiment with infinite cache, the two values converge to 66 bytes. And what that shows, what they found intriguing about that is that, um, over here, so spatial utilization, uh, the limit study at warp and CTA level shows that intra-warp and inter-warp axis contributes equally to spatial locality.
Hmm.
While most of the interwarp locality, or I'll get to the CTA part, but pretty much you would expect that there should be some discrepancy between the intra and interwarp utilization. But what the study shows is that there's no real difference. The spatial utilization is the same. So you're not really going to gain much out of optimizing for intra or interwarp spatial utilization. And what that essentially means is that if you have a spatial locality predictor, prioritizing instructions from the same thread, right, to run before going to a different thread is not going to get you any more performance than if you were to run the multiple warps at the same time, and not prioritize the threads within the same warp. Uh, I think that's pretty much. So yeah, they go on to intra and inter CTA spatial utilization, and what the CTA is yet again is a collection of warps, and when they refer to intra CTA, they're saying that for a thread that brings a cache line in, there's is there some other thread within the exact same CTA. So from either a different warp within the same CTA or the same warp within the CTA, or is there another thread within the same CTA that's utilizing the data for the cache line that was brought in? And there's also final inter CTA cache line utilization. So for the same SM, are there threads in a different CTA that are using the data in the L1 cache uh, that was brought in for a thread that wasn't in that CTA at all. So what they find out here is that for intra and inter CTAs, they see the values are 79 bytes for intra CTA, and 52 bytes for inter CTA. So this just means that at eviction, you will see 79 bytes of the total 128 byte cache line being used by threads from the same CTA, and only 52 bytes of the 128 byte cache line being used by threads outside of the CTA of the initial thread that called in that cache line. And what we can infer from this is, and that's why I paused over here, while most interwarp locality belongs to the warps from, most of the interwarp locality. So interwarp means that it's going to be in a different warp, whether that is in the same CTA or a different CTA. Most of the interwarp locality is coming from the same CTA rather than a different CTA. So when you have a spatial locality predictor, you're going to want to have optimizations that target both intra-warp and interwarp axes, but you should look at these axes within the same CTA. So pretty much threads within the same CTA should be prioritized before executing threads from a different CTA, because you're going to see greater spatial utilization or a better measure of spatial locality from threads within the same CTA. Does that make sense?
Yeah. Is it because they're just related? You know what I mean? They're working on the same
Yeah.
problem.
So I mean, I would assume they are. I don't know if all warps in a single thread block are necessarily related,
Hmm.
but I would assume they would be in most programs. So I think yeah, to answer your question, I think yes, you would see greater spatial locality between threads in the same CTA, because they probably uh, need data from similar memory addresses
Yeah, and then probably some
and
sort of
memory addresses.
scheduler might be moving them closer together just for improving performance? Or
Probably.
yeah,
Probably. I have yet to go into the internals of
okay.
a
It
GPU
just, it just seems
scheduler,
like
but
just from the old caching days, right? Regular cache type thing. It
Mhm.
it seems it seems like a similar sort of the things you compute with kind of coalesce in one area type thing.
Yeah. I mean, GPUs try to, as I said earlier, they try to coalesce all of
Yeah,
the instructions in a single warp into one transaction, if possible.
right.
Yeah.
Yeah. Okay. Thanks. That's kind of where I was thinking it was working, but just wanted to verify.
Okay. Yeah. So they do the same thing for L2 cache. And what they find here is actually kind of the opposite. So what they find out here is that the final intra and interwarp spatial utilization for the realistic 128 kilobyte L2 cache is 63 bytes and 76 bytes. But for the infinite cache, it's approximately 69 and 82 bytes. What this shows is that um, there's a much higher level of interwarp spatial utilization than intra-warp spatial utilization. And going on to the CTAs, they find that the final intra and inter CTA spatial utilization for the realistic um, L2 cache is 66 bytes and 73 bytes, respectively. While for the infinite cache, you see 73 bytes and 82 bytes, respectively. That what that essentially shows is um, that interwarp accesses contribute more to the spatial locality seen in L2 cache,
Hmm.
and most of the interwarp locality uh, that we're detecting is uh, belongs to inter CTAs rather than intra CTAs. So over here it shows that it's inter CTAs use about 82 bytes as opposed to intra CTAs that only use 73 bytes of the entire cache line, showing that inter CTAs have a greater spatial locality. That coupled with the fact that the interwarps have greater spatial locality, uh, shows that it's pretty much the opposite. Because in L1 cache, we saw that the inter and interwarp spatial utilization was pretty much the same, but we saw a much greater amount of intra CTA spatial utilization, showing that the um, most of the interwarp utilization seen in L1 cache came from the same CTA, from
Mhm.
other warps in the same CTA. But if you look at L2 cache, most of the most of the spatial utilization coming from other warps are from warps that are the outside of the exact same CTA. And the reason for this is pretty simple. That L2 cache is a shared resource across all SMs, which means that all of the CTAs and all of the warps from all of the different SMs are accessing L2 cache. So you're going to have a greater probability of seeing CTAs from another SM come in and use the exact same data or spatially local data uh, that you see with interwarp utilization. Does that make sense?
Is there is there something scheduling or co-locating these things automatically, or is this just a one of those features that they observe over time? That certain things cluster together, if you will. I don't know if that's the right way to
Yeah, I
term it.
think I think at the time of this paper, I mean, they're mostly trying to find kind of optimizations that aren't inherently already like built into the scheduler. So I'm assuming
Right.
that this is just behavior that just shows up over repeated experiments.
Okay, so they ran all these various experiments, and they see this kind of co-locality type thing. I don't know if it's called
Yeah.
locality, but
So yeah,
optimization of location.
mhm. They see a lot more spatial locality uh, in between different CTAs than
Right.
they would from the same CTA. And that's just because that's mostly attributed to the fact that L2 is a shared resource across all SMs.
Hmm.
Yeah.
So
Uh,
it doesn't have anything to do with the specifics of the code they're rendering. I mean, well, it
I
must
mean, we
have
can look
somewhat
at
to do with that. Yeah.
graphs. Yeah, I'm sure it does. But if we look at most of these graphs,
Hmm.
in this particular experiment, I don't think the infinite size versus um, regular size is that important. The two metrics that we're really going to be looking at are the interwarp and interwarp. So if we
Hmm.
see over here, like if we compare the green bar to the blue bar, we see that for most of these workloads, we see that the green bar is usually on average a little bit more than the blue bar. Yes, you will see some anomalies like this one or these, but when they averaged it out, they found out that the interwarp spatial utilization was 13 bytes more, which I mean, out of 128 is about 10% more, I would say.
Okay.
So, yeah, I mean, yeah. Does that clear your
Yeah, that
question?
that kind of confirms, I guess, what I was thinking might be going on. Anyway.
Okay. Um, Going on. So they want to look at hit and miss rates. Uh, and they look at it in four categories. They look at interwarp, intra-CTA, and intra-CTA. And what this pretty much does is, I mean, you have spatial locality, you have temporal locality. They're both locality that you can optimize for. But what this does is it kind of gives you like a high level view of where most of the locality is coming from across all of these workloads. So we see that for L1 cache, if we look at warp level hit and miss rates, we see that with normal or with realistic cache size, you have 31% intra-warp and 43% inter-warp hits. And if you combine together, you get approximately around 74% hit rate, which means that there's a miss rate of 26%, which this paper tries to use CPUs as a benchmark. And
Hmm.
the paper claims that CPUs have a hit rate that's typically between 95 to 97% for L1 cache.
Hmm.
So this kind of goes to show that it's extremely difficult to exploit data locality in GPU caches due to the small size of the cache and the massive amount of threads that are running in parallel that each especially in a memory divergent workload need totally different uh, data or data located in vastly different memory addresses present in the cache at the same time. So there's a lot of thrashing, there's a lot of contention. Um, the figure here shows that if we were to now run the same locality study on a L1 cache with infinite size, we see the hit rate actually goes up to 96%, which is a lot more than the 74% that we saw with the realistic cache size. So what this shows is that GPU kernels do actually have locality to exploit, but the current GPUs or the GPUs at the time of this paper are kind of confined by their cache size, and they can't really fully exploit it. So and then after also they show that uh, in previous literature, apparently it's a pretty common assumption that There's more higher intra-warp locality. So this number is going to be significantly higher than the interwarp locality. Um, but what they find in the actual paper is that even with infinite cache, even with realistic cache, the figures are pretty close by. I mean, you have 50 and 46 in infinite cache and 31 and 43. So there isn't like a crazy difference, um, or at least not as much of a difference as characterized in previous literature.
Hmm.
Um, they say that in this paper, this kind of observation is probably due to the fact that they're looking at memory divergent workloads, because the memory divergence workloads, they have scattered memory accesses, and this essentially means that one, there's not going to be as much intra warp locality,
Mhm.
and this also might mean that interwarps or different warps might might need scattered memory accesses to the point where they're accessing similar addresses to a totally different warp. So that's the reason that in this paper, at least, we're seeing that intrawarp and interwarp hits are near equal, or pretty close. They also studied the intra and interwarp hits for L2 cache. I don't think they made any significant findings, but the average intrawarp and interwarp hits were 30 and 15%. They saw that obviously with infinite size, this goes up massively to 65 and 21%, which pretty much means that they go from 45% to
Mhm.
86%, um, which is a pretty big leap. But I mean, that's to be assumed with infinite cache size, and that's not something that they can really optimize for. But the main takeaway from this section of the study is that there's higher interwarp hits at the L1 cache in contrast to previous literature, and that this is pretty characteristic of memory divergent workloads because the entire study is trying to find out how GPUs can optimize for locality in memory divergent workloads. If we look at CTA level hit and miss rate, we see that for L1 cache, at realistic and infinite size, uh, there's 68% intra CTA hits and 5% intra CTA hits, which pretty much shows that most of the interwarp hits from this section of the study, right? The uh, 43% of interwarp hits, or hits coming from outside of the same warp, it's this is most likely a warp within the same CTA. So 68% intra CTA hits. When they continue to look at the numbers for infinite L1 cache, they see that 91% of the hits are intra CTA and only 5% are inter CTA. So they see that most of the locality to be exploited really comes from the same from threads and warps in the same CTA, as opposed to another CTA. This kind of reaffirms one of the previous discoveries, which is that spatial locality predictors should be optimized to look at inter and intra-warp um, spatial utilization within the same CTA. So they kind of summarize this here. The CTA level hit rate confirms a higher intra CTA locality at the L1 cache and inter CTA locality at the L2 cache. So they did L2 cache. Oh yeah, they did L2 cache over here as well. Um, and what they found for that is that for Infinite L2 data cache inter-CTA hits are 13%, which shows that there's potential for better scheduling. So, for example, if we can schedule such CTAs on the same sum, there's a possibility to exploit more inter-CTA locality at the L1 data cache level. So I think pretty much what that's saying is that the L2 cache has a lot more inter-CTA hits than the L1 cache. So, I mean, in the infinite cache study, we saw that only 5% of L1 cache hits are inter-CTA. But if we look at L2 cache, 13% of hits are inter-CTA. And what this shows is that maybe we could increase the locality of, or we could take advantage of this locality present in inter-CTA hits by taking the different CTAs that might be scheduled on two different SMs and pretty much scheduling them all into one SM. So this kind of like I'm going on a bit of a tangent, but I've been working with Nsight for a little bit, and what I found is that it's I don't know if it's impossible, but it's pretty tough to schedule the same a bunch of warps on the same SM because the scheduler will pretty much spread them out evenly amongst all the SMs. So
Hmm.
there's a possibility that there could be locality exploited between two different CTAs or two different thread blocks scheduled on two different SMs if they were put in the same SM. And the L1 cache, they could use the L1 cache instead of the L2 cache, which could boost performance, if that makes sense.
So you're saying they're why are they spreading it out just for total optimization of the hardware
Yeah,
or
yeah. So I mean, I've seen that there's no way of, or at least from my experience, there's no way of if you have like a certain number of threads and they're
Mhm.
packaged into thread blocks. Let's say you run enough threads for to fit into two thread blocks, right? There's no way of telling the NVIDIA GPU, hey, I want both of these thread blocks to run on the same SM. Uh, Rather than running on two different SMs,
Hmm.
right? The NVIDIA GPU will just automatically take these two thread blocks. It'll say, okay, there's thread block one, thread block two. They would be running. They would be running in parallel, but they would be running on different SMs. So if we were to look at cache spatial utility, right?
Mhm.
Most of the spatial utility between these two thread blocks is going to be mostly seen in the L2 cache, not L1 cache,
Oh, I see. Is that
because the
do you
L2
think
cache is shared.
Is
Yeah,
NVIDIA just saying that's fast enough or
yeah. I think that's pretty much their view on it. But yet again, I'm still doing like the observations into this. If I
yeah.
find out anything, I'll update you guys. But I think that's the state of affairs right now.
Okay. So
As we speak.
this is not changed because this paper is what like 22 or something like that or
Yeah, 2022. So three
2022.
4 years.
So but you're still observing this behavior today though.
Yeah, so I think pretty much what it is that they don't see enough inter CTA locality or in between in the L2 cache for them
Hmm.
to say, okay, we should make it possible for scheduling through two thread
Gotcha.
blocks on the same SM.
Yeah, it's probably just not
That would, yeah.
high enough on their task. You know, it's like they don't see the bang for the buck type thing.
Yeah.
Yeah.
Um, So yeah, we go on. So this is pretty interesting. So what they did here is they looked at so disregard figure 12. That's from the previous section. The primary figure of the section is figure 13. And what they did here is they tried to see how much of a speed up in terms of performance are you getting with a larger cache size, right? So for each of these kernels, if you were to increase cache size, how much more performance are you seeing? And what they found is that is figure 13 shows the speed of what the results show that the performance of the memory divergent benchmarks increases up to 6.3 times and on average 1.62 times with more cache size. And the performance doesn't degrade in any case with greater cache size. So, I mean, you can see that some of them don't gain a whole lot from having more cache, but there isn't like a significant loss of performance either.
Isn't that kind of expected behavior though? I mean, why would you expect to lose performance if you increased
Yeah, I
cache?
mean,
Just the overhead, or
I think it's just a thing that they noted. I agree with you on the fact that I think it's pretty intuitive that you
yeah,
wouldn't lose
yeah,
performance with more cache size.
okay.
Um, but yeah, so they mentioned that although not all benchmarks gain in performance, the increase in data locality will save resources such as cache capacity, memory bandwidth, which can be used by other concurrently running benchmarks or to save power consumption. So this section is also pretty interesting. They pretty much give you two improvements that they recommend based on all of their inquiries or all of the experiments that they run. First thing is that they pretty much say, okay, for sectored caches, the current approach is that it's purely demand based, right? If a certain instruction needs a memory address, it will be brought into cache, right? And there will be like a set amount of memory addresses brought in with it, right? Sometimes this won't be necessary. Sometimes you know this it might not have enough data, right? So sometimes you'll see an overfetch and sometimes you'll see that there's a miss because a memory address that is just a little bit more than the sector length could have been brought in but wasn't. So what they're trying to say is that if we were to be able to predict spatial locality for a certain application, we'd then be able to change this protocol of demand-based sector fetching or cache line fetching from to kind of change the amount of data brought in based on the application's exhibited or predicted spatial locality. So, I mean, we can just read through it. Based on the findings of the limit study that GPU based on the findings of the limit study that GPU L1 and L2 caches have much higher spatial locality than currently exploited by GPUs, we see an excellent opportunity to improve the spatial utilization of caches and performance of GPUs by fetching sectors into a cache based on a spatial locality predictor. Current generations of GPUs employ sector caches and fetch only those sectors of a cache line that are required at the time of issuing a memory request. While a sector cache design can save significant overfetching of data compared to a non-sector cache. So if you didn't use sectors, you would bring the entire 128 byte cache line into cache, and that might be a gross overfetch because half of the bytes that you're bringing in, as we saw like earlier in like in the experiment with the 50% of the L1 over here I believe. Yeah, so 50% of cache capacity is not used with current cache line fetching. Right. So if we were that kind of justifies the need for sector-based cache fetching, but sometimes fetching just the sector can underfetch, and you might have to issue another memory transaction to bring the data that you need. When in the first place you could have brought in multiple sectors into the cache and not have had to issue a separate memory transaction for it.
Okay.
Does that make sense?
Makes sense to me. It's always, all these things are always a trade-off, right?
Mm-hmm.
Yeah. So I see what they're
Yeah.
trading off here.
So it is still a conservative design. So while a sector cache design can save significant overfetching compared to a non-sector cache, it is still a conservative design. Misses the opportunities to exploit higher spatial locality present in GPU caches. Our limit study shows that final spatial utilization of L1 cache is 82 bytes, which is 24% higher than the final utilization seen with default cache size, and 76% higher than the initial spatial utilization seen, regardless of cache size. If we only fetch sectors based on initial utilization, which is how it's currently done in current GPUs, there will be significant lost opportunities for exploiting locality. So what this section is essentially saying that with cache size bottlenecks, we see that there's 65 bytes of cache line utilized before eviction. But if the cache line wasn't evicted, or if there was no overfetching, and there was a better uh, you know there was a better method of fetching sectors, then you would have a cache that pretty much would only evict a line if there was absolutely no re-referencing that was going to happen. So that's what this 24% difference shows. That oftentimes, because of overfetching or because of non-optimal cache line fetching, uh, you see a lot less spatial utilization than you potentially could. If we only fetch sectors based on the initial utilization, which is how it's done in current GPUs, there will be significant lost opportunities for exploiting locality. Moreover, we need to issue additional memory requests to fetch missing sectors of the same cache line. A table-based spatial locality prediction has been proposed to improve the cache design of CPUs. While it will be interesting to explore the possibility of adopting a table-based spatial locality predictor for GPUs, the more recent approaches, such as using deep learning to improve GPU architecture, might be more accurate and performance efficient. In any case, our limit study at warp and CTA levels further help to improve the design of the predictor by providing significant insights about the entries that should be cached in a table-based design, or the features that should be explored in a deep learning-based predictor. So what they're essentially saying is that when they looked at the inter and intra warp spatial utilization in the L1, they saw that okay, inter and intra were the same, but then every single time that we saw inter warp utilization, a majority of it was coming from intra CTA threads, or yeah, intra CTA threads. So it would be more optimal for the spatial locality predictor to prioritize these warps that are within the same CTA, as opposed to looking at warps from different CTAs. That's just one of the examples from the study.
Cool.
Then it says warp scheduler. The other improvement that they recommend is warp scheduler improvements. GPU warp scheduling is a well-explored area, with different schedulers typically taking warp and CTA level locality into consideration while making scheduling decisions. For example, Rogers et al. Shows much higher intra-warp locality than inter-warp locality. Hence, the proposed warp scheduler also gives priority to intra-warp accesses. But in contrast to the previous work, they saw that intra and inter-warp hits were pretty much very similar, at least for memory-divergent workloads. So this is possible for memory-divergent workloads, as scattered memory accesses and threads from different warps can access data from the same cache line. This can happen more frequently for memory divergent workloads compared to regular workloads. Therefore, we see another possibility to improve the warp or CTA scheduling decisions by taking the memory divergence of an application into account. So I think the one other interesting point was that Nsight, I think, the paper at least mentions that there's an NVIDIA profiling tool that actually uses or can find the coalescing efficiency of of whatever thing you're running. So what the paper is suggesting is that if we took this coalescing efficiency that kind of characterizes the memory divergence seen within a certain application, then maybe we could write the scheduler in such a way that it takes into account this the fact that an application is more or less memory divergent and thus can prioritize inter or interwarp uh, utilization more. For example, if an application was not memory divergent, then according to the previous literature, they would want to prioritize intra warp hits or interwarp local or utilization, spatial utilization a lot more, or spatial locality a lot more than interwarp spatial locality.
Okay.
Um, a simple memory access pattern sampler could be employed to figure out the type of workloads, memory divergent versus non-memory divergent, indicating the difference in the data of workloads. A locality-driven warp scheduler can adjust the scheduling decisions as per the sampler information. The main goal of this work is to study the data locality of memory-divergent workloads in detail. We leave the potential architectural improvements for the future. Um, yeah. So this pretty much just summarizes it. It shows you a table down here that
Mhm.
summarizes all of the different metrics that they kind of look at. So they initially looked at reuse for L1 cache. They saw there. It's kind of trying to find show you the difference between um, the limited cache size and the infinite cache size. What jumps or what differences we see in these different metrics if granted more cache size. And yeah, so I mean, with most of these metrics, you'll see that there's an increase, there's always an increase, except for like maybe down here, inter CTA hits.
Yeah.
Um, but
But
yeah,
that's not too surprising, right?
yeah, it's not too surprising. I mean,
Yeah.
more and more cash is it's just
Yeah.
better.
But it's just
Uh,
expensive as all get out.
yeah, yeah.
Yeah.
So yeah, then they go into related work. They have two sections.
Hmm.
The related work on locality and GPU caches, and then related work on divergence. So yeah, several works report that hardware managed caches play an important role in the higher performance GPUs. It is also well known that exploiting locality is crucial in GPUs. Otherwise, hardware managed caches can also cause negative performance. Sometimes the use of caches can degrade performance. There have been several studies which show that bypassing caches could lead to higher performance. However, to the best of our knowledge, there is not much work done to quantify the locality in GPU caches. So I think this is just them saying, okay, this is like there's a bunch of previous literature and a bunch of other stuff
Hmm.
related to locality and GPU caches, but our paper produces new knowledge to make quantitative metrics of this locality.
Right.
Um, Rogers et al. Proposes a cache aware warp scheduling mechanism based on estimated intra warp locality to capture locality that is lost by other schedulers due to excessive contention for cache capacity. They reported that the majority of data reuse observed in highly cache sensitive benchmarks comes from intra-warp locality and therefore giving priority to intra-warp instructions to access the L1 data cache.
Okay.
Uh, so yeah, Lee et al. Quantifies the percentage of the inter-CTA reuse, which is based on the data reuse of all the memory requests generated from streaming multiprocessors before they enter L1 cache. Um, yeah, so I mean, it just you're not going to find any like results. It's just really just goes into what are the
Hmm.
other studies done
Yeah.
in
Cool.
locality and GPU caches. Same thing for memory divergence, and they just restate everything that we
Yeah.
just went over in conclusion. So that's the paper.
All
I hope
right.
I this is my it's my first time really deep diving into to a paper like this. So
Yeah.
I hope I didn't disappoint. But if there are certain
No.
questions, I can try to find the answers and then come back with them next time. But
Okay.
yeah, I don't know. I don't know if anybody has any questions.
Yeah. Anybody? Any questions for Srinivas?
No, actually, one thing that I noticed, Shreyas, I think you made this point earlier. I don't know when. You said it's better to increase the size of L1 cache rather than L2 cache. And I noticed that, Blackwell, for example, they have a facility by which you can actually adjust, you can tune how much of shared memory versus L1 cache you use. They allow that you can actually define how much of L1 cache. You can increase it at the expense of shared memory for each SM. So some of these papers are useful to arrive at those design decisions, even in the modern GPUs.
Yeah, that's pretty cool.
Yeah, a
That's
good job,
interesting.
Shreyas.
Yeah.
Thank you so much.
Yeah, I enjoyed it. Yeah. Anybody else have any questions for Shreyas? Okay.
I was in and out during the last half, but it sounded like at least where from NVIDIA's perspective, trying to push that utilization, or sorry, the 43% number, the cache reuse is not
Yeah.
something that NVIDIA is or like numbers on cache reuse may or may not have changed, but it doesn't feel like it's a priority when you're working on stuff at work, as opposed to AMD, which seems to be like taking a very like aggressive stance on trying to
Optimized
increase
for
that.
cache reuse.
Was that kind of what your experience has been?
I don't know. I've primarily worked with NVIDIA GPUs. I haven't worked with that many AMD GPUs, so I don't know.
Well, for NVIDIA, does it feel like there isn't much focus on this sort of like cache reuse? Or is it...
I don't think so. That's what I'd like to say, but I don't know.
Yeah, well, yeah. End of the day, you're not gonna know for sure. It'll just be like a general feeling. Yeah, the thought being there, yeah, like either they feel like they've solved it to like Pareto frontier in terms of it's not worth dumping more money into to squeeze out those last extra percents, or it's like, we've got enough other stuff going on where we don't need to worry about this yet. Which is interesting. Just a thought, I suppose. But thank you. Yeah, it was a great prezo.
Yeah.
Thank you so much. Thank you so much for attending. I know today was a pretty eventful meeting outside
I
of
apologize for the stuff on the front end. Yeah.
We live in
Oh, no
interesting
worries at all. I think it was super entertaining, if I'm being
Okay.
completely honest. So,
All right.
Guess we
I'm
better
going to stop the
subscribe to it.
recording right now then.